This is another example of using containers. And then I'm going to look at a simple machine failure model. I asked you about a slightly more complex one, but I'm going to go through and look at a simpler version of that. So that might give you some assistance in doing the written assignment. And then I'm going to look at a tandem queue with blocking, which is, again, another model which adds some complexity to how it progresses. Okay, so, all right. So here's the idea. And this is also part of the approach of iterative modeling. The multiple server queue model that we has a lot of hidden assumptions. In fact, every model that we have has assumptions which can be more or less hidden. In the basic multiple server queue model, every customer that joins the system is essentially stuck there until they get service. And there are situations for which that really is the case. If you're say going to the drive-through at In-N-Out Burger, once you get in that lane and there's a car in front of you and a car behind you, you're basically kind of stuck. On the other hand, sometimes you observe a system and you see customers waiting in the queue, and then some of them start to get a little fidgety, and then every now and then one of them just kind of looks at their watch or their Apple Watch or whatever it is that they have on their, they look at the time and they leave the queue. In other words, whenever we join one of these lines, especially if it's just kind of us and we're not stuck there with people in front of, like with the car where you might get stuck in a line. Sometimes if it's possible and you've been waiting too long, then you leave. And then if we observe that, we notice that everybody who leaves after a different amount of time. In other words, each person, if you think about it, and this applies to all of us, we might have this kind of internal clock or this internal alarm clock that says, how long are you willing to wait in this queue until you get service? Now, we may not be aware of it, but if we observe this behavior, we notice that for everybody, it's slightly different. And so the amount of time that each person is willing to wait, is presumably some aspect, some parameter that they have. And then, they decide to leave. And that in the queuing terminology, that's called reneging. Reneging is kind of when you kind of Welsh on a deal. And the idea here is that if I join a queue with the idea of getting service, then I've kind of reneged on the deal that I was going to get service. So again, it's called reneging. And the thing is, none of the models that we have capture that. The multiple server queue model does not capture that. We had a slight element to that with the finite capacity situation, where an arriving customer looked at the line, and if there was no room for them to join it, then they would leave. That's actually called balking, as we said. And again, think of the In-N-Out Burger, where the line is all the way out to Del Monte Boulevard, and so you really, if you're being a good driving citizen, you don't join because it would block the road. But this is different. This is, we join the queue and then at some point we leave. So how can we capture this? Well, let's, here we have the basic parameters for our multiple server queue. The number of servers and the service times. Again, we're not looking at the variable thing. And of course, that aspect could be added, but we're just focusing now on the renege. And so now we have a sequence of these renege times, which suggests that when it's implemented, we're going to use a random quantity for that. Again, keep in mind that these sequences that are indicated by the curly braces here are typically going to be modeled using a random variant in the code. Okay, so now what might we be interested in this? Well, the first two state variables have to do with the tallying of customer times. So this kind of builds a little bit on the model that we did yesterday. So we have the number of available servers, and then we have now something similar. Now this is a little bit different. The queue yesterday, the queue container was containing the arrival times because we wanted to collect explicitly what the delays in queue and the time in the system, and to do that we did the times. Here we're really interested in keeping track of the unique customer, and so instead of keeping the times, what this container is going to do, it's going to keep the unique customer IDs, and it's initially going to be empty. And we'll see why. Well, basically, what's going to happen is we want customers may leave the line in the middle, and we want to make sure that whichever customer is scheduled to leave is the one that actually leaves. And then, so that's why we have these unique customer IDs. So how can we give every customer a unique ID? Well, we'll see. If you think about it, there's a natural way that comes from our friend, the arrival process. So now and actually these two measures are enough to actually make the model work, but they're not quite enough to get the measures that we would be interested in. Now, if you're the manager of this facility, what might we be interested in? Well, speaking for myself, I would be concerned that if the lengths of the queue was too long, that I was losing too many customers because they got impatient. I mean, it's like that restaurant that nobody goes to anymore because it's too crowded. You've heard of that one. Yeah. Yeah. Yeah, I like the comments. All right. So what I'm interested in is what proportion of customers am I losing because of this? In other words, if my queues were short enough, then even my relative, I would lose only a very small proportion of extremely impatient customers. On the other hand, if my queues are too long, then I'm going to be losing too many. And so this model could help me understand what the impact of this is. In other words, this is one of these indirect impacts of having a long queues. And so if I count the number of customers who renege, let's call that R for renege, and the number of customers who receive service, for some reason I call that M. Why? I have no idea. There's no M in service, or there's the only M in here is in number and in customers. So I have no idea why I called it M, but doesn't matter. I mean, the labels are fairly arbitrary. Okay, so let's look at events here. So now the idea is our arrival event now is going to have an argument, and that argument is going to be the unique ID. In other words, I'm going to assume that every time I get an arrival event, that its argument is going to have the unique ID of that customer. Now, when I start service, what I'm going to do is I'm going to pop that guy off, and actually I don't really do a whole lot with it, but popping it off is actually removing it from the queue. So the size of the queue goes down by 1. I decrease my available servers. That's fairly typical. And then here I'm throwing the server back again, very familiar, and I'm incrementing the number. Remember, M was the number served, so I got that here. Again, we had our run event. That's probably where I should have started. But here's the new event. The new event, I'll call it renege, and I'm going to give it an argument. And the argument is the ID of the customer who is reneging, that is leaving. So first, I want to count another reneging guy. So here's another guy another customer who's lost. And now, instead of popping, I'm removing that particular customer from the queue. Okay, so those are my state transitions. And the event graph looks like this. And this is it's an illustration both of using a container as well as a canceling edge. We've only seen a couple examples of canceling edges, but this is kind of an important one. So let's take a look at how this works. So when an arrival event occurs, again, keep in mind the argument is the ID of the customer. We add them to the queue. Now we do two things. One is if there's an available server, we'll schedule start service as we always have, but we're also going to do something else. We're going to take his renege time. So this is how impatient, this is how much time this guy is willing to wait. And again, in the implementations, this is going to be a random variable. We're going to generate from a new random variable. Now I'm going to schedule my renege event with the delay of this renege time. And I'm going to pass it this argument, the parameter I, to the argument. Okay, remember that whenever an event has an argument, we must schedule it with a parameter. And we designate that with a little box on the scheduling edge. That is, this always has to be there. If we left this box off, it would be incorrect. And unfortunately, well, when we're doing this either with a drawing program or a pencil and paper, there's no compiler to kind of fix it for us. And unfortunately, even in NetBeans, the compiler isn't going to help us there because these scheduling edges use a wait delay, and so the compiler has no way of knowing that whether or not we've put this parameter on or not. So that's just something to watch out for, and that's why running in verbose mode is kind of important. Okay, so here's where the canceling edge comes in. So the idea is that every customer who's in the queue has a corresponding renege event on the event list whose argument is their ID. So when I pop this guy off, when I pop his ID off, I now cancel the renege event, passing it that argument. Now remember that for canceling edges, if I want to make sure I'm canceling the right event, if the event I'm trying to cancel has an argument, I need to pass it a parameter on the canceling edge as well. So this I that I popped off, that's the ID of the customer. And since it had previously been added when that customer arrives, that means that there is an I on the queue. And so when I cancel this, this says, find the renege event whose value is this one, and just remove it. That is, not remove it from the queue, remove this renege event from it. Okay, and then everything else is kind of the same. I schedule end service, and if the queue is not empty, then I schedule a start service again. So this piece right here, just this one event right here, together with this scheduling edge and this canceling edge, add the ability of this model to capture the number of reneges, the number of customers that I've lost. And so if I look at the value of R, the number of reneges, over the number who have actually served, then I get a decent, I get an estimate of the percent of customers that I've lost due to impatience. And the impatience, I mean, if your impatience is like a few seconds, and depending on what system you're looking at, I mean, if we're, since we're used to fast computers and fast internet, if we hit a web page and it takes more than a few seconds to load, then we may bounce off to another page. So that's just something that that doesn't exactly correspond to what this is about. But again, this what we're doing is by simply adding a couple of state variables, one event, a scheduling edge, and a canceling edge. We now have we're now capturing something about our model that we hadn't before. Okay, so now all that's great. However, you might be asking, well, one of the other measures that we might be interested in is something that we can't quite capture with this, and that is of the people who renege, what is their average time in the queue? And of the people who get service, what is their average time in the system or time in the queue? Okay, this model doesn't do that. So we're going to need actually an extension of this model in order to capture that, and that's actually something that is going to be the subject of the next computer assignment that I'm going to give you. But there's one little thing that we need to fix on when putting this model together, and that is notice that this arrival event has an argument I. And what that means is that a plain old, there are two things that need to happen here. First, a plain old arrival process. Remember, an arrival process just by itself produces events that are called arrival, but they don't have an argument. There's no argument here. And so a plain arrival process is not going to cut it for this. The other thing is that I need to have a process by which every arrival event has a unique argument. That is that unique customer ID. Because if they're not, then things are going to get confusing over here. If these aren't unique, then this scheduling and canceling stuff is not going to work. So how can I do that? Well, since you asked, I can take my basic arrival process, and remember that the arrival process had as a state variable the number of arrivals. And since the number of arrivals is always increasing, never decreasing, that means that the number of arrivals is actually the first customer, second customer, third customer, et cetera. That's a unique ID. And so at least conceptually, what I can do is I can simply take that value and schedule an arrival event passing that number of arrivals. So the first one would be 1, second one would be 2, third one would be 3, et cetera. Now, unlike the array thing, this would be based on, this is one base. So the first customer has an ID of 1, second customer ID of 2, et cetera. That's perfectly fine. See, if we did it, even if we did it by 2s, the key here is that these guys are unique. It doesn't even matter what they are, as long as unique. So if for some reason we decided to increment this by 2, it would work just as well. Okay, so
Arnie, if we're drawing this on our own, you'd have this subsection, the subcomponent here off to the side to demonstrate the first portion, and then the second portions off to the other
Yeah,
side.
you mean this? You mean like this?
Yeah.
Yeah, yeah. And this is really kind of open to how should I say? This is small. This is so small that if you wanted to, you could. There's nothing wrong with just writing this component as it is right here. That's just saying, forget about anything we've done. What we need, we have a parameter that are our inter-arrival times. We have one state variable here. You could just write this component from scratch, and there's nothing wrong with that. This would work perfectly fine. It's not a huge amount of code. However, again, the being lazy, what I like to do is, given that I've already done this, the laziness says, well, I don't want to have to do it again. So if I write this from scratch, I find I'm writing all the code that I had in here again. And the principle of laziness says, well, if I'm writing the same code again and again, then maybe there's a better way. Well, there's a different way. I won't say better. So again, if this makes more sense to you and you want to do it like scratch from here, that's perfectly fine. There's absolutely nothing wrong with that. On the other hand, if you're lazy like me and want to do it this way, then and we've seen a couple of examples of this where we've subclassed our arrival process. We've overridden the due arrival event, making sure to call the super, and then we just schedule our arrival with, in this case, the parameter n. And in the subclass, we actually have two choices about how to do this. I don't have the code to show you, but this is where, if you remember, we used protected for the state variables. I'm not sure if I'm spelling this correctly, but remember, protected instead of private. So why protected? Well, one of the reasons is that now in this subclass we can have direct access to the state variable. And so when we do this, we can just say it would be wait delay arrival 0, and then number of arrivals. We could do that. If we didn't, we could still use the getter. That would work fine too. So we have our choice. And again, neither is more right than the other. But that's why having the state variables be protected allows subclasses to have direct access to that state variable. In this particular case, it doesn't matter since we're simply using it. There are other situations where we actually want a slightly different state transition, for one or two events. And in that case, it is important to have it be protected. Okay, so that's, and as I said, now the one thing that this doesn't do is, as I said before, if I'm interested in also estimating how much time the guys who reneged spent in the queue and how much time the people who got service spent in the queue, this doesn't do that. Remember that the multiple server queue with explicit tallying that we did yesterday saved the arrival times. Now I could do that here by kind of having another queue that saved the arrival times and then did all that stuff. But there's actually a better way. And that better way is I'll begin talking about that in the second part of today's class. But before then, I just want to quickly go through another couple models. And see, what we're doing here is we now have all of the machinery for these event graph models. We have the machinery of event graph models. We have some, but not quite all yet, of the machinery of SimKit in order to implement these. But what we really need is some, and what I'm presenting are just more examples to give experience in how to do this. In other words, between this and then the written assignments that I torture you with, the idea is that to really put this in your toolkit, to have the ability of looking at a situation and being able to represent it as one of these discrete event graph models, it requires some experience. In other words, it's not enough to just learn all the vocabulary. If you want your thesis, when you write it, to be written well so that whoever reads it is going to have an enjoyable experience with it, then you need some experience in writing. So in order to become the good writers that you are now, you've done a lot of writing. I mean, if you reach this point in your graduate studies, you've at least done a certain amount of writing, so that when you get down to writing your thesis, it will have good grammar and flow nicely and everything. So how did you get to that point? You got to that point by just doing a lot of writing. Likewise, for doing this kind of modeling, the way to do it is to get experience with a bunch of different models in different situations, and have, just have some patterns that you can put together, but not be blindly, just kind of doing. Okay, so this is a simpler version of the problem that I asked you. So be careful, be cautious about just taking this hook, line, and sinker. But this is a simpler version of this. So we have a bunch of machines that periodically fail, and now, unlike the question that I asked you, the idea here is that the machine operator is also the repair guy. So in the question that I posed to you, the machines are either operating on their own, or the operator is not the repair person. So there's a separate resource of repair people in that situation. Here, the machine operator, there's a machine operator, and if the machine breaks, then the machine operator can immediately begin repairing it. So there's no queuing here. But the key thing with both this and the situation in the written assignment I asked, it's an example of what's called a finite calling population. And what's different about this is that, unlike the queuing situation where we have an arrival process coming, one of the hidden assumptions of an arrival process is that there's actually an infinite calling population, meaning that no matter how many people show up to your system in that situation, they keep coming at the same rate. The difference here, and if you think about it, so let's put a number in. So let's say set m equals 3. So let's say that there are 3 machines. What is the, and we can think of the machines as customers, kind of. When all machines have failed, what's the next arrival? And the answer, there isn't one. If they've all failed, then there are no more to fail. So your model needs to take that into account. What that means is that the arrival process is not a good model for this situation. Okay, so what is? Well, let's look at parameters. So first parameter, number of machines. Okay, that's a given. And then what we have the times to failure. So once a machine is up and running, it's going to have a time to failure. And that's true of every physical system. It's true of non-physical systems as well. But things wear out, things fail. If you run a machine, it's at some point it's going to fail. Maybe a long time, but it's going to happen. And then when it fails, it's going to require a certain amount of time to repair. Okay, so our state variable is, we'll call it the number of failed machines. That really is all that we care about, because our quote servers might be the people who are operating and repairing the machines, but that is a quantity that doesn't change. In fact, the number of operators is always in the system exactly equal to the number of machines. So there's no point in even defining a new parameter, and it's not going to be a state variable because that's not going to change. The only thing that changes is the number of failed machines. So, so now this is actually a very simple set of state transitions. So I only have one state variable. What could happen? Well, initially it's 0. And then I'm going to schedule, did I say M? This should be 0, sorry. Yeah. So number of failed machines, we'll start off with everybody running, in other words. Okay, so what could make this state variable change? Well, a failure. So I get one more failed machine. And what could cause that to go down is we finish repair. And that's, now we could put start repair in too, but I mean, basically a failure is the same as a start repair. So there really wouldn't be any point. Now, the thing is that we also need to have M failures on the event list at first. So this handles all the state transitions that we want, but it doesn't handle the initial failures. In other words, at time 0, if every machine is working, there need to be M failure events initially. And we know how to do that. And this is where it's, this is where kind of the event graph version of a for loop is important, because we need to schedule all of those. And the only way to schedule an event in an event graph model is with another event. Okay, so we're going to have to use this sort of init guy to schedule the initial failures. And what does that look like? Okay, so first, this is our for loop here. So this is all, we've done all this before. So what's going to happen? The run event is going to schedule init passing at 0. And init is going to schedule a failure with a failure time delay. And then it's going to schedule another init as long, passing an I plus 1 until as long as I is less than M minus 1. So at the end of this, init will have occurred M times, and so there will therefore be M failure events on the event list, all at different times. So again, it's not the order that we schedule this, it's the order that they appear. And since these failure times are typically going to be random, then they'll occur, whenever they occur. Okay, so now what happens when a machine fails? Well, since the operator is the repair person, they can immediately begin repair. How long does it take to repair? Our repair time T sub R. So we would schedule an N repair. And then when N repair occurs, we now have one less failure event, but it's going to fail again. So we have to schedule another failure event. With what delay? Another failure time. So basically the way these things work is, what is it that causes a machine to fail is you repair it. So the lesson is, if you don't want a machine to fail, then don't repair it. It just like if you want your computer to be 100% safe from viruses or hackers, then shut it off, lock it in a safe, and never turn it on. And I promise you that it will never get a virus. However, if you want to use it, then you need to kind of open yourself up to that vulnerability. Likewise, if you don't want your machines to fail, then don't fix them. But on the other hand, you won't have the machines to be doing the job that they're there for. So again, this is like one of the simplest models that we could have, but it illustrates an important point. And that is that the arrival process that we've been using a lot for does not adequately capture this finite calling population. Again, notice that there's no arrival event that occurs with a self-scheduling. The only self-scheduling edge is this init. And once that's done, we never see init again because nothing schedules it. Once this condition fails, is false, then no init gets scheduled. And then notice that the only thing scheduling init is run, which happens once at the beginning, and the other inits, which happen just at the beginning. After that, this is the way that the model operates. Okay, so this is just a simpler version of what I've asked you to do. So there are pieces in here that might help on that regard, but again, if you just take it lock, stock, and barrel, it's not going to be correct because in the question I asked you, the machines, it's not enough. They can't begin to be repaired immediately because they have to basically queue up for the repair people, and it's the model I asked you was slightly more complex. Okay, so I think I can start this, but then I'll probably have to finish this after the break. So this is another, remember we talked about, we've had tandem queues where we have the customer or the part leaves one station and goes immediately to another station. And then for a particular system we're looking at that has that basic structure, so we have two workstations in tandem, meaning parts arrive to the first one, they queue up. When they get service, they don't leave, but they go to the second workstation. But the problem is the second workstation has a finite capacity. Remember we had the finite capacity queue where arriving customers would bulk. But here we don't have that possibility because we need to process all the parts. All the parts have to go through the first station and then the second station. But the problem is that these parts are these may be fairly big parts. And when it's finished at the first station, there may be no room to move it to the second station. In other words, there may be only a certain amount of room to move the things off. This could be a physical constraint, and that's typically what it is. Okay, so now the part that's leaving the first station wants to go to the second station, but it can't because it's blocked. In other words, the queue is full, so it can't move on. So what happens, again, because these are big things, and so what happens is the part has to stay on that first machine, which means the machine cannot process the next part because it's got the old part on it. So it's not working on it. It's just sort of sitting there, but it physically can't move off until things get unblocked in the second one. So in other words, the part is blocked from proceeding, and it can only move forward when there's an opening at the second queue. That is when it becomes unblocked. Okay, so let's try to model this. Again, we can, I'll be taking a break before we get to the final thing. But just as with our tandem queue, we have the number of machines in the first station, number of machines in the second station. Okay, that we've done all that before. And then we have the service times at the first station and the service times at the second station. Again, we've all done that before. And then the one thing that we've added is the capacity of the second queue, meaning that that's how much room there is in the second one. And we're going to assume that that's bigger than 0. We're going to assume that there's at least room for one of the parts to be in that second queue. Okay, the state variables are, again, very similar. So we have the number in the queue at the first station, number in queue at the second station, both initially 0. We have the number of available machines at the first station and the second station. They're initially equal to the total number of machines. But now we have an additional state variable. And that's going to be the number of blocked parts. In other words, the number of parts that are blocked at the first machine and can't move on to the second machine because there's no room at the end. Okay, so we have this additional state. We need this additional state variable because, remember, the state variables that we have for the queue and the number of available machines do not capture the full situation. In other words, looking at the first station, before, when there's infinite capacity in the second station, when we finish at the first, we just increment this. And so now this machine becomes available. The problem is that if the part cannot move on, that machine is not available. And in fact, what we do is we have one more block part. So when we look at the events on that, sort of again, always start with run. So we have run with we initialize our state variables, the queues to 0, the number of block parts to 0, and then the number at each of the number available machines as starting with the one number. And things look very similar to start. So in arrival, we increment our queue at the first station. When we start service, we decrement the queue and the number of available machines at the first station. And then likewise, and just for layout purposes, I did this kind of backwards. Let's ignore B for the time being. But when we arrive at station 1, then we're incrementing the first queue. And then once we start service, we have this is all familiar. So this is all part of the multiple server queue piece. But here's where the difference is. So what we're doing here is when we end service at the first workstation, we are simply saying, okay, we're going to say we're going to start off by being blocked. All right, so now we have we're not going to assume that that part can move off. We're just going to say, okay, you're blocked for now. But then when we get to arrive at the second workstation, again within that we're calling 1, now this is where we unblock. So we say that now we have one fewer blocked part, and now we do have our available server at the first station. In other words, we cannot say that the machine at the first workstation is available until it gets unblocked, until we can move the part off. So you see that? So just because, remember that in our previous models, we'd always said end service would increment the available servers, but now what we're calling end service has a different state transition. And in the past, when we've had arrivals, we've only incremented the queue at that station. We hadn't done this. But the lesson here is that none of these are just sort of boilerplate. None of these state transitions, none of these events are laws of nature. They're not written in stone. They're dictated by what happens in the model and how the model is trying to capture what's happening in the system. So again, the way we're doing this is that even though in the past an end service would have this state transition here, we can't do that because when we finish service on a part in the first workstation, we don't have an available server yet. But what we do have is we do have a block part. We do have one more block part. When we can arrive, when we can kind of move on to the second workstation, then we can unblock. That's what this is. And now we can have our available server. It's getting cluttered, so let's. Okay, do you see that? And so the event graph now has some similar things, but again, all right, so arrival, S bigger than 0, we've done that. Start service, schedules end service, but then notice that there is no scheduling edge from end service back to start service as we've done before. So again, like with the scheduling edges too, they're not something you just automatically put in. You have to really think through, does this really make sense? So if our end service event at the first workstation simply increments the number of blocked parts, then we can't schedule a start service, because supposing at this point there aren't any available servers, machines on the first workstation. In other words, when we finish service, all the other machines were busy as well. So if we try to schedule this, even if the queue is bigger than 0, I mean, so you may be tempted if you're to say something like this. All right, but if it is quite possible that at this event, S0 is equal to 0, and if we do this, if we schedule this, Q0 could be bigger than 0, but if we schedule this now, this state transition will drive S0 negative. It will now be -1, and so that is not what we do. Well, what can we do? Well, when we finish service, we can check to see, is the second queue less than its capacity? Remember, we had a similar constraint when a similar Boolean condition at the finite capacity queue. And it's exactly the same thing. If there's room in the second queue, then we can schedule this arrival to station 1. And when that happens, we unblock, we now have an available server, and we now have one more in the second queue. But now that we have an available server, we need to check, well, now that there's an available server at the first station, we need to say, can we process another part at the first station? The answer depends on the queue. If there's some waiting in that first queue, then we can, so we schedule that. But in addition, since we have also incremented our queue in the second station, then since we've arrived there, we want to make sure that we have that we can start service. And under what condition can we do that? If there's an available server at the second station. Now let's look at this state transition here. Okay, and we've seen this state transition a lot, but now look, Q1 is now decremented. In other words, we've taken a part from the second queue and we've now put it into service, and there's now room in the second queue. So if there's a blocked part, we can schedule another arrival now. And in the meantime, we're also processing our first part, this part at the second station. And then when we're done, maybe process one there. So look at this sequence of events. It is quite possible that when things get all blocked up, the only thing that's going to unblock it is going to be, we finish service at this second one. So imagine that, we're all blocked up, everything, and everything in the first station is ground to a halt because all the machines are stopped processing. There are parts waiting to be processed, but they can't be processed because there are no available servers at the first one. Why? Because everything is blocked. So what could cause that to be unblocked? Well, an end service here. So that gives us one more available server. And if there are a bunch of blocked parts, then that means that there's got to be parts in this queue. So this will schedule a start service at the second station. And then when that occurs, that means that we'll take a part out of the queue, which in turn is going to schedule an arrival here, which unblocks. And now we have an available server, which in turn will schedule a start service at the first one, which then will schedule an end service, et cetera. So in other words, one of the things that we need to make sure about in our system is that when things are just completely blocked up, there's a sequence of events that will unblock it. So that's what this does. Okay, so that is it for the first part. And so let's see, it's 5 till. We'll take a 10-minute break and come back at 5 minutes past the hour.